So last lecture, we ended up, at the end of last lecture, we were looking at the fusion reactions that are going on inside stars. So these are the fusion reactions going on in the core of our sun. Now, I've gone back a few slides here to pick up a few items. First of all, these we said are the reactions going on inside the core of the stars. And that all three of these reactions are going on all the time. And we said that there was a certain amount of energy release, Q, for each of these reactions. This first reaction, really important because it generates neutrons and stabilizes them inside a nucleus. So that's kind of the source of all of the neutrons that we're familiar with now in nature. Comes from these reactions happening inside stars. It's not very energetic. The deuterium is not especially stable, just stable enough to get those neutrons locked into place. So these were the reactions. And then we had gone through this in a good amount of detail, so just wanted to bring this up again. Taking two of the first reaction, two of the next reaction, one instance of that third reaction, and then taking the net, canceling out what's being produced. So we said this first reaction produces some deuteriums along with some anti-electrons. Those deuteriums get used up in these reactions, and now we have some helium-3s, and the helium-3s get used up in this reaction to form helium-4, and then all these other materials are getting recycled. The anti-electrons end up reacting with electrons, which are in the plasma at the core of the star, and that gives us additional energy. So here was the net effect from the fusion reactions, and here is the net effect from the matter-antimatter reactions. And we calculated Q values on these and got a net Q of 26.74 MeV. And we said that we're getting pretty close now to, with this set of reactions, we're almost at 1% of the mass being converted into energy. Very, very measurable in these fusion reactions. Now here is the net effect of the fusion reactions themselves. Now this reaction we have here is not entirely charge balanced. So I've got 4 hydrogens coming in, I've got a helium coming out. Now if I'm just thinking of nuclei, then I've got 4 plus charges here, 2 plus charges here, and 2 here, and this equation works. But if I'm thinking of the electrons too, then I also have 4 electrons here, 2 electrons here, because 2 of those electrons have reacted with the anti-electrons. So this, what I think of as a pretty interesting feature of stellar energy generation is, about 10% of the sun's energy is coming from matter-antimatter reactions. So that's kind of interesting. Now, heavier stars that have more mass, have more extreme conditions in their core. Higher temperatures, higher pressure, fusion reactions are happening at a faster rate, and they can generate more types of elements. And so these fusion reactions go beyond the fusion reactions that we would have with just the formation of helium. So here is an outline set of additional reactions that are going on inside stars that have more mass. So what does happen, and maybe we mentioned this in the last lecture, is that once helium is formed, helium-4 in particular, once we get that isotope of helium-4 formed in these series of reactions, why don't we just have more protons that keep attaching to the helium-4? And it turns out that helium-4 is pretty stable. Remember, helium-4's nucleus has a pair of spin-up, spin-down protons and a pair of spin-up, spin-down neutrons. Both protons are in the 1s state, both neutrons are in the 1s state, and that makes for a really stable nucleus. turns out that the next set of elements, lithium, beryllium, and boron, just don't have the same level of nuclear binding energy that helium-4 has. So there's kind of these elements you have to kind of skip past somehow in order to get something else that's more stable, and that next isotope of stability is carbon-12. So heavier stars are able to take 3 of these helium-4s and pack them together into carbon-12, but kind of low mass and low to medium mass stars aren't able to do that, at least not early in their lifetimes. And so helium becomes kind of a termination step until conditions within the star become more extreme later on during the development or the evolution of the materials in the core of the star. So with these heavier stars, once they get some amount of carbon-12 generated, they can go through these additional steps. So once they get to carbon-12, well, nitrogen-14 is pretty stable and oxygen-16 is pretty stable. So now we have some number of stable isotopes of carbon, nitrogen, and oxygen. And you can see there's this more complicated series of steps. The end net effect of all this is still the generation of helium. So we're not yet at the step where we're producing large amounts of the carbon, oxygen, and nitrogen. They're just behaving kind of like a catalyst. It gets produced in the reaction, but then it gets used up in a subsequent step. So we can ask the question then, what would be the heaviest element that would be produced in fusion processes inside stars? Now, from our nuclear stability plots that we've looked at a couple times now, what we found was that the most stable nuclei that we have are like iron-56. And so if we start with kind of the simplest elements, the simplest isotopes, and keep adding more protons and neutrons on, we can keep releasing energy all the way up through iron-56. So the heaviest stars, the high mass stars that are out there, are able to, there's enough gravitation to create extreme enough conditions in the core of those high mass stars. We don't expect the sun falls into that category. We expect that the sun, later in its lifetime, not currently, but billions of years from now, when kind of the hydrogen fuel runs out and the core is filling up with a lot of helium, gravitation will collapse the core somewhat, creating higher temperatures, and a good portion of that helium could fuse into carbon, nitrogen, oxygen. But the highest mass stars create even more extreme conditions and are able to fuse elements all the way through iron and release energy in the process. Now, once you get to iron, these higher mass stars can fuse elements beyond iron, but instead of that releasing energy, that now requires energy. That utilizes some of the energy. It actually cools down the core. So with the loss of energy being released from fusion reactions, the cores of these stars gravitationally collapse and they supernova. They have an explosion. The star is blasted apart. And during the supernova explosion itself, additional heavy elements can be produced. Now, if you look at abundance of different elements and their isotopes across the periodic table, once you get past, kind of that fourth row in the periodic table, once you get past iron and copper, zinc, some of those elements, the abundances of those elements and isotopes just drops off dramatically. So again, high mass stars generate all those elements up through kind of the fourth row of the periodic table, but it becomes more and more difficult to have heavier and heavier elements generated. We feel like some of those get generated in the supernova explosion itself, can generate a range of heavier elements beyond iron, nickel, copper, zinc, and then other extreme stellar reactions like mergers between neutron stars or whatever. There could be other extreme kind of situations that are also able to produce heavier elements. All right, now we want to move on and start looking at possible fusion reactions that we might be able to utilize in a nuclear fusion power plant. So kind of the joke in this is that when will nuclear fusion plants be available? And the answer is always, about 10 years from now. And that's been going on since I was a kid. So when I was a kid, I was interested in this stuff. I'd go to the library at the school I was at and try and search for books on nuclear energy, and you'd find these books saying that within 10 years we should have nuclear fusion power plants, and that these nuclear fusion power plants are going to produce plentiful energy, clean energy. We'll have our energy needs met for the foreseeable future. And fusion's still 10 years away. It's always 10 years away before we learn how to manage these. Now, the problem is that nuclear fusion requires some extreme conditions. We've got to get, in order for nuclear fusion to occur, we've got to get past that electric potential energy barrier, that repulsion between positive charges of one nucleus and positive charges on the other nucleus. We've got to be able to overcome that. When we do some calculations, we find out fusion reactions would occur at really high temperatures under extreme conditions, and those have been difficult to create and sustain, and that's what researchers have been trying to do now for 50, 60 years, create some kind of a containment vessel where the fusion reactions can occur and we can continue to maintain those fusion reactions. So these are three of the reactions that are considered possibilities. We don't start from protons. Remember, those first reactions with protons require us to make neutrons in the process. That requires the weak force. That's not a rapid process. So we would start off with deuterium or tritium, for example. If we start off with deuterium, we can generate tritium. We can generate hydrogen-3, and then that hydrogen-3 could be used in other reactions. And if you look at the Q values on these, the Q values on these first two reactions involving two deuteriums, that's pretty good in and of itself. And then using tritium, bringing tritium into the reactions, boosts that quite a bit. We're getting like 4 times as much energy or more, 4 or 5 times as much energy by running that third reaction. So these reactions are considered to be, possible fuels using deuterium or tritium for a fusion power plant. All right, so let's take a look at our fusion power plant. Let's look at that last reaction. That one looked kind of interesting because it involved deuterium and tritium being used. So let's take that last reaction. It also had a really high Q value. Now, when I went through and I did all the masses, I looked these up online, and these are the numbers that I saw coming out for deuterium, tritium, helium-4, and neutrons. And so I used those numbers, carried out a Q calculation, and the Q value on this gave 0.01888 atomic mass units. I used the 931.5 conversion to find out how much energy that corresponds to, and I ended up with 17.59 MeV. So a really large amount of energy for this deuterium-tritium fusion reaction. Now, in a power plant, are there concerns? Are we generating something that's radioactive? Well, tritium is being used along the way here, so tritium is being generated. Now, tritium also gets used up in the reaction, but there is some amount of radioactive tritium being generated. The other issue is, notice that in this reaction in particular, and I think some of the others, we're generating neutrons. So neutrons are a bit of a concern. If we have a lot of neutrons coming out in the reaction, those neutrons are going to get absorbed by other materials in the reaction vessel, and additional neutrons can turn something into it can make them radioactive. So if different materials in there are absorbing neutrons, that could turn them into radioactive isotopes of that element. So there's still some concern here, maybe with some radioactivity being generated. But the products themselves aren't inherently radioactive. The tritium is, I guess, but again, the tritium is going to get reused in this reaction if possible. So here's the Q values, and the Q values are really high, so I wanted to go in and do another one of those calculations of determining what fraction of the mass is being converted to kinetic energy. In the fusion reactions, in the fission reactions, we were seeing that almost 1 part in 1,000 was being converted. And now in these fusion reactions, we're seeing even higher rates. So to calculate that, this time I did it just in terms of mass. I said the Q, in terms of atomic mass units, 0.01888 atomic mass units. Here's the mass of the deuterium that we put into that reaction, and here's the tritium. And I ended up with 1 part in 266, and so that is about 0.375%. So it's not as high as it was in stellar fusion, and that's because the stars were starting out with just protons. We're starting out with some nuclear binding energy already in place. But still, that's pretty remarkable. And so let's get back to our power plant. Now, the numbers I'm using for the power plant were the same that I used in the fission example. So let's see how that compares. We had a 1,000 megawatt power plant operating at 33% thermodynamic efficiency. It's just boiling a bunch of water and generating a bunch of steam to turn a turbine and run an electrical generator. And so we had calculated that we would, during a year, so I need to write 1 year in here, write that in. 1 year of operation would produce 9.6 10 to the 16th joules. Now I'm converting that to MeV, same as before. This time I'm doing the calculations a little different. What I'm trying to find out is how much deuterium do I need and how much tritium do I need. So I want to find out how many times I'm going to run this reaction. How many times does that reaction need to run in order to generate all the energy for the entire year? Enough thermal energy to operate our power plant. So I did this. I said each time we run the reaction, that generates 17.59 MeV of thermal energy. And that means we have to run that reaction 3.41 10 to the 28th times during the course of a year. And so I calculated for the deuterium and the tritium, if I run that many reactions, I'm going to need the same number of deuteriums, same number of tritiums. And then I took their molar masses and converted that into grams. And between the grams in here, I divided through by 1,000 to convert into kilograms. And what it turned out is, for our power plant, our reasonably, good-sized power plant, I'm going to need only 114 kilograms of deuterium and 171 kilograms of tritium, and that's it. I just need a few hundred kilograms I think in the fission plant it was like 1,300 kilograms of uranium. Well, we're only going to need a few hundred kilograms of hydrogen and of deuterium and tritium. Now the tritium, the deuterium, it's around. It's in water, for example. What other sources of hydrogen do we have? Anything that has hydrogen in it, some of that hydrogen is going to be deuterium. Now deuterium is, compared with hydrogen-1, deuterium's abundance is really, really low. It's like a tiny fraction of 1%. So, but hydrogen itself is fairly abundant. Again, we have a lot of hydrogen in water. We have a lot of hydrogen in other types of organic compounds have hydrogen in them, and that, some of that's going to be deuterium. So years ago, when my youngest was in, I think it was like 2nd or 3rd grade, he came home from school one day and he said, "Dad, do you want to come on a field trip with my class?" And I said, "Sure, where's the field trip?" And he said, he pulled out his paper and he was reading it and he goes, "We're going to the nuclear engineering department at the University of California, Berkeley." And I go, "Really? A 2nd grade class is going to go take a tour of the nuclear engineering facility? Count me in. Definitely want to be there." So we got there and they gave us a tour of the facility. And one of the questions I had, of course, was, how expensive is deuterium? You're running all these tests on possible fusion type reactions. And so I had to push some 2nd graders out of the way because they had questions too. But I made sure I got my hand up and questions answered. And the person there, if I remember right, this was years ago, the deuterium was pretty inexpensive. He said, you get these tanks of deuterium, and they were like $40 or $50. I guess I should look and see if it's still that price. Maybe I'll look on Amazon and see if they're selling any deuterium. But in any case, it was pretty cool to take that tour, and the deuterium is pretty readily available. It's even though it's very low concentration, it's different enough. Its mass is so different. It's twice as heavy as standard hydrogen. It's pretty easy to sort out the deuterium using different like centrifuge techniques or whatever. So anyway, you can start with a bunch of deuterium, run some of these other reactions to generate the tritium, and you don't need more than 300 kilograms of fuel to operate this power plant for the whole year. And you're not left with an enormous amount of radioactive leftover debris. There's some radiation issues to deal with, but maybe not so severe. So we'll see, 10 years out, we'll have these nuclear power plants figured out. Now, another example we want to take a look at is what are the conditions, what are the temperatures at which deuterium and tritium would just run into each other and run these reactions. So we can come back and look at the potential energy barrier for that. So here's that very same reaction, and the atomic numbers are both 1, and the nucleon number is 2 for the deuterium and 3 for the tritium. And so I've gone back and used our potential energy barrier, our electric potential energy, electromagnetic potential energy barrier, and did the same calculations. We've done these before. And so I've carried through the numbers. And down here at this step, I ended up with, well, here are the 2 radiuses for the deuterium and the tritium. And it gave us a number of 0.444 MeV. So that doesn't seem so bad. That's much lower than some of the other examples we looked at. But what temperature, at what temperatures would, if we get these hydrogen up to these really, really high temperatures, at what point would fusion be significant? And here's kind of a rough estimate we could carry out. Let's say that the kinetic energy of the deuterium and the tritium atoms in our reaction chamber need to have roughly kinetic energies equal to this number. That would mean that the fusion should be happening pretty readily. And then we can borrow a formula from thermodynamics that the average kinetic energy is roughly given by 3/2 kT, where K is Boltzmann's constant. From that, we can do a temperature calculation, and it turns out that we're looking at temperatures of 3.4 billion Kelvin. So that's a pretty high temperature. Now, we don't actually have to go to this temperature. At this temperature, the reactions would be proceeding pretty readily, because on average, any deuterium and tritium pair would have enough energy to react. We could run at we could run at lower temperatures, where we're mostly getting the fusion just from the high end, the deuteriums and the tritiums that happen to have enough energy to react. But that's giving you kind of an order of magnitude. What are the conditions inside the cores of stars? There are billions of Kelvin. The surfaces of the sun, surfaces of stars, surface of the sun, it's like 5,800 Kelvin, 5,800 Kelvin. That's nothing compared with temperatures inside the core where the fusion reactions are taking place. All right, so a successful fusion reactor is still 10 years into the future. That's what we keep telling ourselves. One of the ideas for that is to get a reaction vessel. One of the common configurations is kind of a torus shape, kind of a donut shape, where we can get, using magnetic fields, we can prevent the deuterium and the tritium from cooling down. If the deuterium and tritium gas bump into the sides of the containment vessel, they tend to transfer out a lot of their energy. And so we're trying to come up with some kind of a configuration. So here's actually what was at the beginning of the chapter. And there's a person standing down there, just to give the kind of a scale as to how large this is. So this is some research facility, I'm not sure where. There have been a handful of these built. And you can see there's kind of this torus or donut-shaped opening here, and that's where the deuterium or the deuterium-tritium mixtures are contained. And we're using magnetic fields, and they're using kind of radio energy broadcasts to transfer a lot of energy into those samples. Now what's happened is researchers have been able to set off fusion reactions, but they're not able to sustain them for long periods of time. So typically, fractions of a second, they're able to get these fusion reactions up and running, but how do we sustain that over long periods of time? So that's kind of what we're left with. Now the last topic that we're going to be taking a look at in this chapter, so we looked at fission and fusion pretty thoroughly, and some different types of reactions, nuclear reactions. And now what we want to do is look at radiation effects. And so first of all, there are some units of radiation which I think we should never use, we should stop using them. But unfortunately they're in some of the homework problems and they're in our textbook, and so you just kind of have to be familiar. 1 curie represents a decay rate of 3.70 10 to the 10th decays per second. So I'm not planning on using that, but you guys need to be familiar with that to be able to do, again, some of the homework problems. So here's an example that they gave us here. And what they're saying is that we have a sample of phosphorus 32, which is radioactive. And instead of telling us how much mass or how many numbers of nuclei we have in our sample, they tell us the sample has a certain decay rate. So that's a common way that these problems are set up, is they're set up as some type of a decay rate. Let's see how that works. So here's the problem that they're talking about. We're using phosphorus 32, and if you go back and read that last slide more carefully, I moved on, it says that we're using it in a biological setting. So we've got some kind of a, maybe it's some kind of phosphate that we're placing a bunch of cells in, and we're seeing if the cells are actually able to uptake some of the radioactive phosphate that we've put in there. So the idea would be make some kind of a medium that we can grow these cells, these organisms, in this medium with radioactive phosphorus, and then after some amount of time wash off the cells and then sample the cells and see how much of the phosphate has been taken up. That's how the problem's outlined. Well, here's the reaction. It's a beta minus decay process, and the half-life on this phosphorus 32 is 14.27 days. So this is something in the matter of days, and that's useful because once some number of weeks and months go by, this stuff will have mostly decayed. We will have to deal with it over a reasonably short time. Now here is that Curie's stuff, and I put some question marks here, and I had some issues with. Anyway, they've given me 0.016 micro Curies. Now the micro is 10 to the minus 6, and even though the symbol here is Ci, it actually, the word here is Curies, and it's named after, well, Marie Sklodowska, who is known as Madame Curie. I always thought that's funny that this person is referred to as Madame Curie when Curie was actually her husband's name, and her name was Marie Sklodowska, and she was Polish, and so I always feel like instead of being Curies, they should be Sklodowskas. Anyway, so 0.016 micro Sklodowskas, and then I'm going to do that conversion that was on that previous page where it says 1 Sklodowska is 3.70 times 10 to the 10th decays, and that has told me that, oh, you know what they really meant to tell me is that the decay rate is 592 decays per second. And I don't know how you guys feel, but I feel like that is ever so much simpler to think about than to think about these units of microcuries or microsklodowskas. All right, so I've got a sample. It's currently decaying at this rate. Well, that makes me wonder what its mass is. And so I know how to carry that out from chapter 41. We can use the half-life, convert that into a lifetime, and I calculated the lifetime in days, and then I calculated it in seconds, and then later in the problem I needed that in hours. These are all just different units that I'm using for to represent the decay for the lifetime, the lifetime constant. And so if I take that lifetime constant and multiply by the decay rate, which they told me, that works out to be 1.05 times 10 to the 9th. That also seems like a simpler way to start the problem out. Instead of this 0.016 microcuries, microsklodowskas, they could have told me it's decaying at 592 decays per second, or they could have just told me there's 1.05 billion of these radioactive nuclei in the sample. So that number actually that's kind of interesting to think about. So if there's only a billion of these phosphates, of these phosphoruses, how many cells do we have, and how many of these are the cells actually going to be taking up? Anyway, let's take a look at the mass. So I carried this one step farther and calculated the mass by taking the number and multiplying by a molar mass. Now it's phosphorus 32, so the molar mass would be 32 grams per mole, and that gave me a number of 56 femtograms, 10 to the minus 15 grams. All right, so I think these are the important things that I want to say come out from this problem. How many decays per second were there? How many nuclei were present in the sample? And how much mass did they have? How many grams or femtograms of phosphorus 32 were there? All right, so the sample itself, we were told, is, it says that we waited 1 hour between the time that we put the cells in the phosphorus until we washed away the medium that we had put them in, the solution that we had put them in. And since that's only 1 hour and the half-life is 14.27 days, what I found out was, it started off at 592 decays per second. After 1 hour, it hasn't dropped much. It's at 591. So it's almost the same decay rate it was before. Now, we're expecting that the full sample then, after that hour, we would be, or after that 1 hour is 591 decays per minute. We're expecting that that is going to be, let me go back and check this. So what the 720 is coming from is right here. That's what we're measuring. 720 counts, but it's per minute from the cells. So what we're saying is, if all the phosphorus had been taken up, we would have expected a decay rate of 591 decays per second. Instead, what we're seeing is only 12 decays per second. That's only about 2%. So by taking the observed number over the total number, we can find out what fraction of the phosphate was taken up. Only about 2% of the total phosphate was taken up, or the phosphorus. I'm assuming it was in a phosphate compound. All right, so let's move on from there. We also, kind of as a last topic here, is we want to look at what's called radiation dose. And I'm just going to move ahead to this next slide here. So this is my radiation dose diagram. And what we're saying with this is, let's say that we take some different sample. Actually, here's a person. We're taking some material and we're sending a bunch of X-rays. And we want to find out, or we want to have a measure of how much of an effect those X-rays had on the material. How much of a dose did those objects acquire from that radiation? And so the way we define dose is this. We say, what is the total amount of energy of radiation that went through that material? So what's the energy of radiation that passed through the material? And then how much mass was there in the sample? So the idea then is, if we set up kind of a standard set of X-rays and it's a pretty good sized beam, you know, it's pretty wide, whatever we place in that beam, in some sense, is going to pick up kind of the same dose. Depending on what size it is, that's going to determine how much energy is absorbed from that radiation. Now, the official unit for that is called a gray. The short, the abbreviation for that is big G times Y. So 1 gray is 1 joule per kilogram. And it turns out that for some biological systems, for us, for example, a dose of about 10 gray is actually lethal. If you receive a dose of 10 gray over a short amount of time, there's enough cellular damage that you won't survive that radiation exposure. So let's think of this as an example. Let's say that we have a cup of water and we want to make some tea or something. We want to boil the water, maybe make some coffee. But the microwave is broken and we don't have anything else to heat something up with. But wait a minute, there's an X-ray machine down the hall. What if I go down to the X-ray machine and I take my sample of water and I put the X-ray machine onto the water? Is there a way I could just heat up the water using an X-ray machine, using an X-ray source, instead of microwaves, for example? And so here's some water. I put it at 20 Celsius, just as some kind of a reference. Now, this would take us back to specific heat calculation. So we could say this. We could bring back Q is equal to mc delta T. Now this Q that we've got here, this is Q from thermodynamics back in physics 4b. What we're saying is there's a certain amount of heat transferred into the water. And what I want to know is this 10 gray exposure, is this, lethal dose of radiation, is that going to be enough to heat up the water to a useful temperature to make some coffee or tea or something? So I solve this as delta T is Q divided by MC. And for the Q and for the M, what I put in was the lethal dose. I said, okay, 10 joules per kilogram, that's going to take care of Q and M in the calculation. So the only other thing I got to put in besides the dose is the specific heat. Now that's 4,000, that's a comma, 4,186 joules per kilogram per Kelvin. And when I calculated the delta T came out to be 0.00239 kelvins. And I did put some exclamation points there. So it turns out a lethal dose of X-rays would have almost no effect. Even though the water has absorbed the equivalent of what would be a lethal dose for an animal or a plant, maybe an animal, is barely heating up the water at all. So what's going on here? And there's a couple things to be aware of. If you take some water and you just heat it up, from some kind, using microwaves or something, you're not breaking any chemical bonds. You're rotating the molecules if you're putting water in a microwave oven, for example. So if you're exciting the molecule in terms of vibrational quantum states or rotational quantum states, that doesn't take the molecule apart. The molecule still functions. But when you're using X-rays, all of the energy of the X-ray, these X-rays could have 10 million eV, that could go in and break hundreds of thousands of chemical bonds. So once you get past even UV photons, you start to create molecular damage because the molecules are being disassembled. And it doesn't take much energy. If I have 10 gray going into this 1 kilogram sample of water, that's only 10 joules. For a biological system, if you have a person that's 50 kilograms, 500 joules of X-rays are lethal. You go, 500 joules, that's nothing. That's not going to even warm the person up noticeably. They're not going to feel the effects from that. And again, it's because all the energy is coming in the form of high energy photons, and all of that energy is available to break a bunch of chemical bonds. Okay. Now, the reason that 10 gray is lethal is that 10 gray is enough to damage cells that are in the process of dividing. And in humans, for example, and other animals, our blood cells are being generated inside the bone marrow, and those blood cells are constantly, the stem cells that produce the red cells and the white cells and the platelets out in your circulatory system are produced by stem cells inside the bone marrow. So they're producing all of these cell lines. Red cells last for like a month or something, and then they get recycled, and white cells and platelets probably comparable. And so if you take out the bone marrow cells, then your bone marrow stops producing new generations of red cells and white cells, and that turns out to be lethal. Now, what you can do for someone exposed to 10 gray, well, their stem cells in their marrow are gone, but you could give them a stem cell transplant. Now, that's actually what's done in many cancer therapies. In cancer therapies, we want to destroy all the cancer cells. Cancer cells tend to be fairly sensitive to radiation because in many cases, cancer cells are all in the process of dividing all the time. Cancer cells just can't stop dividing. And during the division process, they're especially sensitive to high energy particles coming through, these high energy X-rays and such. And so the idea of a stem cell transplant or a bone marrow transplant is to go to really high levels of radiation or chemotherapies that kill all the cancer cells. Now, the collateral damage is that the bone marrow gets destroyed, but if you've got bone marrow cells waiting to be reintroduced, that takes care of it. So you can a patient can put their own stem cells and store those, and then after the X-ray therapy, bring those back in. Or you could use someone else's stem cells if there's a close enough biological match. So lots of different applications for kind of these nuclear physics radiation examples. Now, not all different sorts of radiation have similar biological effects. We've introduced this unit of gray to kind of measure how much biological effect. And those numbers apply to X-rays and electrons. But notice if you're using neutrons or alpha particles, gray for gray, joule for joule, they can do 10 or 20 times as much damage. And so the damage that you're getting from those can actually be quite a bit higher. So that's considered a quality factor. Now, also in the chapter, I should point this out, there's a lot of units of radiation, and the chapter kind of goes on and on with a long list of units. The only ones that we're going to be looking at, so this is a good example to understand. So you want to know what radiation dose is, and you would want to know that, if something is exposed to some number of gray, you want to know how these units work. Also, calculate temperature increases for different samples of material based on the radiation that they've been exposed to. So the gray is kind of like the only unit we're going to work from in there. Now also, there's a lot of stuff going on at the end of the chapter on different types of medical imaging. It's a lot of descriptive, it's a lot of really interesting material, but again, this is something that you can read as you're interested in, but it's not, if you look at the homework problems, for example, there's nothing really addressing those kind of descriptive portions of the book. So we're done for chapter 42. We're going to end with that definition of radiation dose. So a quick reminder, in chapter 42, we looked at nuclear reactions. We looked at a good number of those. That's got to be important. And we calculated Q values. We found out how much mass is there. We found out kinetic energies and velocities of the products. We looked at fission in a good amount of detail and topics related to fission. And then we also looked at fusion. And again, a good amount of detail I'm going to say on fusion, both inside stars and power plants, as another example. And then radiation dosing. So how much energy is absorbed by an object when it's exposed to radiation, and that's it. So that is this chapter. Questions on any of that? And that takes us through chapter 42. So we'll end with that.